people who are inside this meeting. How to do this are here. So Jungen is online.
Yes, sir, John, I'm on.
Yes, I see you. After that, we have Vorabet. Vorabet is here. Okay,
Yes.
then, yes. Cavicorn, K8, Cavicorn is there. We've got Kritak and KR, KR. No, maybe he or she, Mr. Kritak, and maybe we, did they inform you that this lab is online? Maybe this guy has gone to the laboratory. I afraid. What do you think, this guy? Maybe
I don't
he.
think so.
You don't think so? Okay. Tanagon. But I will not mark the students as absent. Okay, because of this flood situation. Let's see what will happen. Tanagon is there. Notaya. Pichayapon. Yes. Kritsa. KR. Kritsanapong. KR. KR. Hongsuri.
Yes.
Okay, yes. Vatsayot. W. A. Vat. No. Pongkorn. P-O. Pongseri. Pongkorn is there. Okay. Vishnu. V-I. V-I. Oh, maybe this guy actually dropped because he, right? He didn't show up. Maybe he dropped. Herman. H. J. H. Kim Song. K-I. Kim Song. Okay, it's okay because this session is being recorded, and we have 1, 2, 3, 4, 5 students probably, or maybe 4 students who are absent, but it's okay because this is like a emergency situation. So this is being recorded, and these students have the chance to watch this later on. Okay. Now I have a question. Did you see that I uploaded the source code of the previous lab experiment on Microsoft Teams here? Did you see this? Did you notice? Let me show you. Okay. And did you open it? Did you check it? Do you have any question about that? Is there any student who has question, who doesn't understand why a single line of code is there? Why I put this line of code or that line of code? Do you have any? Are you wondering about those codes or not? I think I uploaded it here. Let me show you. Do you have any question about that? You know, when I was a student, the Verilog was so difficult, and I have maybe 100 questions. I remember I didn't understand this Verilog for very, very long time. I had a lot of questions. I think this is CE. Is this one? All right. Up. Yeah, this one. I'm talking about this one. So what happens if you click on this? It needs a lot more. But I think I uploaded it here. Let me check. Yeah, week number 9. Okay. So as you see, I have top module and this counter module. For example, let's open this one for review. Whatever. Downloading. Okay. And where does it go after we download? Download here. Okay. For example, here, the code that I showed you, do you have any question about this? Or you understand every single line? You understand it, right? No question?
No question.
Oh, really? Okay. So I actually added some comment that probably it helped too, okay? But if you still have question, you can ask me in Microsoft Teams. Just send me private message or Just ask here, okay? All right, so let's go to, this is week number 9, right? This is the answer to week number 9. Now we are going to discuss week number 10 online, okay? Online. Annotate PDF. Oh, by the way, I have extended the week number 9 submission report to next week. Is that okay? You don't need to submit today, okay? Oh, and also the files that I uploaded here. Right, these files, let me go back. Week number 9, these files are not complete. These are only 1 and 2 modules, right? So let me show you the modules that you actually have to add. Okay. So this is the top. This is for week number 9, okay? This is the top. Let me change the style of this page style to plain. So this is the top. Right. And this is going to be your CPLD. CPLD. Then your CPLD have an 8 megahertz clock. So I'm going to put it here, 8 megahertz. And this is one pin that goes inside. Then you have reset, right? Reset. Then the output of this module, this is the top .v, top module. The output, this one is 8-bit, and it's going to be the CX. This one is 4-bit, and it's going to be ANX. Okay? And you are going to connect this to multiplexers. Sorry, to 7 segments, 1, 2, 3, 4. Okay, and this one also to control it. Okay, to control the 7 segments. So we have, you can, for example, think about the digital clock, and this become, what time is it now? 9, 0, 9, 3, 6. Okay, so these numbers will be shown on the CPLD 7 segments. We have 4 7 segments. Okay, and then what we have here, let me show you. Top. Okay, then you need to this is your clock divider. Clock divider. Yes.
Came.
What's that?
Kritaka.
Oh,
I
it's
just came. Kritaka.
Don't worry. What's Kritakan?
Yes.
Okay, I thought you gone to the lab. I thought you been there. Okay, Kritakan. All right. Yeah.
Yeah.
So, this is a clock divider, right? And you have to reduce the 8 megahertz clock to 1 hertz. Okay, I discussed this already. And this is when I say these files that I uploaded here are not complete. That's what I mean. It means now you have to actually have a clock divider, let's say .v. Okay, this is the Verilog. Okay, you have to add this. Then you have the reset, and this reset and clock. Okay, this is the clock, 1 hertz, and the reset. Now goes into that 2X, what's the name of the X74 93. Then you have another X74 93. Actually, if you want to show four 1, 2, 3, 4 numbers, right? You have to have 4. But for the week number 9, you can use either these two pairs or these two pairs, up to you, okay? So you need to, then the 1 hertz also go to this one. Oh, no. From here, there's a clock. This one is the clock module. Okay, this one is clock for the small module. Then from here, you have the clock connected to this one and the reset like this. And the output of these things go inside. This is 4 bit, right? This is 4 bit. How to show this? You remember you designed a multiplexer, 7-segment multiplexer, 7-segment multiplexer. It had 1, 2, 3, 4 input, but each input was 4 bit. You remember this? We did it maybe 2 weeks ago, okay? 4, 4. So this is, this is actually how you do it. From here to here. Okay, to here. And we call them via, okay, via. So here, for example, I say point A will be connected to here. Point B will be connected to here. So these two counters will be connected to mux, and the mux actually will be connected to that. Let me clear this. To that CX, okay, and ANX like this. That's it. This is the complete design of big number 9. So what I have given you is this. The code that I have given you is the top, but the top that doesn't, this one is lacking. Okay, inside my code. And also the top doesn't have this. So this is also lacking. Where I get some water? Hold on. So you have to add this, okay? But later on, you come and rewatch this recorded version and pause here, this diagram that I just showed you, and then you can actually simply code it, okay? According to diagram that I just showed you. Now we have this thing here. Let me leave it here because maybe some students will join us. Then open another one. Go to week number 10. Did I upload the week number 10 on LMS?
No.
No, I'm going to do it now. Log in. Which one is it? This one. Yes. So let's go to lab. Week number 9. So let's set, extend the due date of week number 9, which you supposed to actually submit today, okay, to next week. So let me do that. Week number 9, this one, okay, this one, the submission. How about this one? How about the week number 8? I can see only 5 submissions. You can submit late, okay? You keep this in mind that you can submit things late, but you lose a little bit of mark. So next week is 23rd of September. So you can submit from, let's say, 10 to 23rd. Is that okay? But this one, you have to actually show me the numbers, okay? Show me the numbers on the CPLD. I'm gonna put here, okay? Complete week number 9 experiment and take a photo. Oh, this is actually maybe it's hard because you have Can you come to the lab next week, like Monday, Tuesday, Wednesday, or is it still flood?
We hope so, Ajahn. We hope so.
Okay. So, okay, how about this? How about up to simulation? Is that okay? Up to simulation. I'm going to show you what do I mean by up to simulation, okay? So complete week 9. Let me run this while I'm explaining this. Complete week number 9 experiment up to simulation, okay? Then next week when you come, you have the chance to upload it into the CPLD. Up to simulation. Okay, and that's it. Submission setting, everything. Save and return to course. So now actually you can submit it, but up to simulation. What do I mean? I mean this. Let my ISC software. And do you guys have the ISC installed on your PC? Everybody, today, right now?
What is it?
I mean the ISC software. This one that I'm going to show you. Do you have it on installed? Or no? At home? On your laptop and PC,
Oh,
do you have the ISC
yeah.
software installed?
I have.
Can you hear me? Is there any student here who haven't installed the software? If you don't have it, then you have no other choice but to go to the lab, okay, and use the lab's pieces if you don't have it. But if you have it, you can actually do this at home. All right. Now, one of you got this file from me last night. It was, let me see.
It's me, sir.
Yeah, Junggon, right? So,
Yeah.
Junggon, was it difficult or easy?
Not
Easy, right?
Yes, not difficult.
Yeah, not difficult. You see, it's not very difficult. One of your friends or your classmates got the file from me last night.
Yeah,
But
yeah.
But you need to know torrents, okay? You need to know torrent system, and you have to synchronize with me. So I turn my laptop on, and you also have to turn your side on, and then the file will be transferred to you. If you don't have the software, let me know, okay? I can give you the file. So after I give you the file, exactly the way that I'm doing right now, I run my VirtualBox and I run my CentOS, then I go into the system. This is my 123 is the password. I get inside and now I have my ISE on my laptop, okay? Let's go to week number 10. Git, AU, DLD lab, wait. Okay. Let me upload this while this is being so yeah, when you get here, right, open terminal, and then you will see this one, /ru now again, I have this problem. Sometimes I cannot type here. Now I think this is one of those occasions that I think I have to restart this. There's a problem here, don't worry. So I'm gonna shut this down. Okay, there is a problem with this software sometimes. I don't know why. So we are going to power off. Okay, while this is being restarted, I will go and upload the week number 9. AU. No, week number 10. Okay. And week number 10, edit. So we say this is online session due to flooding, okay? And delete, yes, week number 10. Now you can download the lecture note right now. What is this? Hold on. Something's wrong. Something's wrong. What is wrong? Okay, something's wrong. I think my laptop got freeze. Hello, can you hear me, guys?
Yes.
Yes.
Okay, okay. All right, so go here. Now go to the LMS and you should be able right now to see this option, this one. I hide it, okay? Download the week number 10. So we have only 2 more experiments, only 2, okay? Today, week number 10, and next week is week number 11. So today I'm going to teach you everything up to simulation. You don't need to program the CPLD. And then next week, when you come to the class, after I teach you the theory of the week number 11, then you have the chance to upload your code into the CPLD. I mean your week number 10 code into the CPLD. Okay, I think it's all right, no problem. Because I actually used to teach this course 100% online, 100%. So the students never came to the lab. Week number 10, okay. All right. This one is very important, okay? And it has a very detailed and long theory. That's why I said maybe it will take like around 1 hour for me to explain the experiment to you, all right, about 1 hour. And then if you have the ISE software, the one that I'm going to show you, let me rerun this again. At home, then you don't need to come to the lab. You just use your own PC or laptop and the ISE software to code, and then you simulate, and that's it. You can actually give that to me, and or you just come to the lab and upload it to the CPLD. So the only thing missing, because we have an online session, is that you have no chance of uploading the code into the CPLD device. That's it. All right. Okay, so what is this course about? This course is about digital circuits. Okay. Of course, it's a lab, all right? But first, we have to learn the theory of these digital circuits. Now, digital circuits are categorized into 2 major categories, okay? Those who have no clock, those who have clock. Those who have no clock, we call them combinational circuits. In short, CL, or combinatorial circuits. Same, you can use either of these terms, CL, okay? Here we are dealing with a module like this. It has a bunch of inputs and a bunch of outputs, okay? So far, everything we designed falls into this category if it has no clock, okay? If it has no clock, it becomes CL, From now on, I just say CL, CL. Now, if we have a clock, okay, then clock, right? We can keep track of time. Simple clock, right? This is the clock, right? 12, 3, 6, 9. Keep track of time in our circuits using a clock. When I say keeping the track of time, what do I mean? Okay, if I want to, let's say, shopping mall with my, let's say, wife and children, okay? I want to go shopping mall. Then I tell everybody, hey, let's meet each other. I will leave my work at 5 p.m. 5 p.m. Let's meet each other at 6 p.m., for example, at the shopping mall. So myself, my wife, and my children, all of them, we have clock. And what we have to do is we have to synchronize ourselves with the clock. So we can be on time, 6 p.m. we can be in the shopping mall, right? Sync, okay, sync. We have to sync ourselves with the clock. So basically, when we have a clock, when we have the notion of time, then it's very easy for us to synchronize our actions, like going to the shopping mall, like having a dinner. So things can be done together in a certain periods of time. In digital circuit is exactly the same thing. We have something called clock. What is a clock? Clock is just a square like series of pulses like this, okay? And it has a period, fixed period from here, for example, from here to here. Yes, okay, that's the period. And it keeps getting repeated if you pay attention, right? It just now here, the way that I drew this, they are not the same size, but the period of here, the period T should be exactly the same as here, T, okay? So in digital circuits, we have a clock, and then the components sync their action with the clock. This is interesting, right? And that's why we call these circuits that have a clock synchronous, okay? Synchronous circuits, all right? So every digital circuit that you may see in the universe, all of them can be categorized into two things. Those who have no clock, those who have a clock. Those who have no clock are called CL. Those who have a clock are called synchronous because they are synced with clock, okay? And today we are going to learn in a systematic way. What are those circuits that have a clock, which we call synchronous circuits, okay? Now notice that we already use these systems. Like what, can you give me one example? One example of the circuit that we already use, it's synchronous, but because that time we never learned the term synchronous, so I never mentioned it. Can you give me one example? I'm gonna give you in class point too.
The multiplexer, the 7-segment one.
Say it again.
The
Maybe you type. Maybe you, I think hold on. When I ask question, right? I think if you type is better. Just go here, okay? Type here. Type your answer. So I can see the name of the student. Plus, I can clearly understand what you say. 7-segment multiplexing. Yes, Pungseri. Yes, Pungseri is correct. Nice. So let me go there and give it. Hold on. I need to give in class points. Especially this session is important in class points. is this file? Yes, Pungseri. Okay, Pungseri, nice. Okay. Yes. So the counter, for example, that we designed last week is synchronous. That counter. The multiplexer that Pungseri said is synchronous. Okay. Where is it? Oh, here. So here, example of those circuits is, for example, counter. The counter that we just X7493, right? And if you look at the counter, it has a clock, right? It has a clock, CLK signal. So it's synchronous, right? And multiplexer, 7-segment multiplexer, all of them. Oh, be careful, not the multiplexer, the one that actually, the one that drives the CPLD, 4-digit CPLD. It has a clock. That one is actually synchronous, not the multiplexer by itself, okay? All right. So let's see what we have here. Recall that in week number 1, we categorized digital circuits into combinational circuits and sequential. Oh yeah, here actually, okay, back here. So here I talk about synchronous, right? I say combinational and synchronous, okay? But actually the real term is sequential. Let me put it here, sequential. Okay, now sequential is divided into 2 groups, synchronous and asynchronous. Okay, asynchronous. Okay, so sequential comes from the word sequence, right? Sequence means a series of events, a step by step, one after another, and that's it. That's the clock. You see, you do this, and then you do. Let's say you are sensitive to the rising edge of the clock, to here, rising edge. Okay, rising edge. Then you do one thing here in sequence, right? And after one clock cycle, you do something else here. Then after another clock cycle, you do something else here. Okay, so this actually implies sequence. The counters, you count a sequence of numbers, 0, 1, 2, 3, 4. It's a sequence, right? So that's why officially they say, okay, these types of the ones who do things in sequence, right? They call sequential. Those who have clock, okay, are synchronous because they are synced with the clock. But there is another type of sequential circuit that has no clock, okay? But it's not like this one. It's not like this. Why? Because if I want to draw this, right, the in and the out, right, has a feedback into the system. This one doesn't have a feedback. Can you see any feedback like this? No. But this one has a feedback, okay? So that's the difference between asynchronous. But asynchronous, that has feedback, right? We are not going to, this is a difficult topic. You might not even learn this in your master program. It's very actually advanced topic and we don't talk about it nowadays. In 2022, nobody talks about asynchronous circuits, okay? So usually we have synchronous or CL circuits. Now, this is the block diagram of a sequential circuit. Both, you see here, we have 2 types of sequential circuits, synchronous, asynchronous, okay? But in this course, we only use this synchronous circuits, okay? We don't use asynchronous. Now, this is the block diagram. Now here, what do you see? You see a CL block. It's just, when I say CL, it means inside this you have a bunch of, let's say, AND gates connected to inverter, maybe another OR gate, things like that. Okay, a bunch of gates here. Combination. Some gates are combined together, and are placed here. Okay, so here you have the input, and then here you have the output. Okay, but look, this is actually the true difference between the sequential, okay, of type synchronous, okay, versus the CL block is this, that sequential circuits have memory elements. So a subgroup of the outputs can be saved. The result can be saved into memory. And can you see here we have a feedback? And later we can use the information saved into the memory as another set of input into the system. This is input, right? So that's sequential circuit. Now, next one. If I ask you how to implement memory elements in digital circuit. Okay, for example, you are a human, right? I am a human. We have memory. And how can I mimic the exact same behavior in digital circuits? If I ask you that question, your answer says, aha, we can actually implement memory using what we call flip-flops. This is memory. You will learn what they are in this lecture now, okay? And look, every flip-flop must have a clock pulse. Can you see that? The input of the flip-flop, one of the input is a clock. You will see later why, okay? Don't worry. But that's why here I say synchronous circuits. Can you see? Synchronous circuits, they have clock. Okay, but CL circuits, they have no clock. Okay, the reason is this, because the sequential circuits, they need memory. Now, you might say, hey, what do you really mean memory? Can you give me one example? All right, the example is this. If I ask one student, if you were in the class, I would say, hey, you know, just count. Just pointing to one student counting from 0 up to 10. And this student starts counting 0, 1, 2, 3. Then here I say stop. Okay. And then I tell the student to continue counting. And the student say, okay, 4, 5, 6, and so on, right? But how the student could remember to say 4 after the 3? After when I say stop and then continue, right? This is the proof that humans have memory. Now, you remember, I gave this as an example to you when we were talking about counters. So digital circuits who want to, let's say, count, they need to have memory, right? Because counting means always, you see, that's how you count. Let's come back here, okay? Come back here, let me get rid of everything. So if I want to count, I say the initial value, let's say, is 0. And my combinational, no. I say, let's say, whatever initial value from the memory is 0. The 0 comes here, 0. Whatever comes here, I will add it, plus 1, okay? And then it goes here. And I also show it to output. So 0 plus 1 becomes 1. I show the 1. Okay, but I also save it into memory 1. Okay, then this 1, you see, we need a clock. After 1 clock period, this 1 will propagate. So the 0 now is not 0 anymore. It becomes 1. The 1 comes here, 1, and now 1 plus 1 is 2. And now here is 2. No more 1. And this one, no more 1, become 2. So 2 will propagate all the way to here. 2. 1 plus 2 becomes 3. And this becomes 3. This becomes 3. And then 3 propagates, right? 1 plus 3 is 4. And as you see, when I look at the output, right, I can see actually the counting behavior. Now it becomes very clear why you need memory if you want to count. So here I can write like this. An entity which desires to count must have memory. That entity can be a human or a digital circuit. Okay. Now I show you. If it's a digital circuit, how actually it works. First, you have to say the first number, 1, okay, and then the content come here. You perform the addition 1, 2, 3, 4, and you add, right, until up to whatever number that you want to count. And those steps, sequence of steps, right, must be controlled by a clock. All right. So now we understand we have two types: CL circuits and sequential circuits. Sequential circuits, those who have clock are called synchronous. Those who have, they are still a sequence but no clock. Okay, they are asynchronous. We don't discuss them in this course. All right. Synchronous sequential circuits employ signals that affect the storage element at only discrete instances of time. Means just like this, discrete instances of time. If this is the time axis, okay, only like this, ding, ding, ding. This is actually clock, okay? Discrete instances of time means this. Synchronization is achieved by using a timing device called clock generator. Clock generator. Now let's talk about clock generator a little bit. For your final project, you have two options. Most of you went for the TTL. Oh, the afternoon section, I actually the lab technician showed them an example of very good TTL based digital clock that previous students of mine created. Okay, you next week when you come to the class, let me know. I will show you. Okay, remind me. Okay, so you can go for TTL. Let's say digital clock. Okay, you want to design a clock. Okay, you can go for TTL or you can go for CPLD. If you go for TTL, you have to buy ICs. Okay, TTL ICs. If you go for CPLD, then you have to code. It's completely up to you. If you go for CPLD, you don't need to have clock generator. Can someone tell me why? Why is that? Why we don't need clock generator?
We can, we have the code for that, right?
Yes, yes. Yes, who is talking here? Who is, I want to give in class one. Who is this? Pungsri, again, Pungsri. Yes, because as you see, we have, when we code, right? The code supposed to be uploaded into CPLD, and the CPLD has an 8 megahertz clock generator, crystal clock, right? It has a crystal oscillator, 8 megahertz, and then you just code, you connect your module to the pin. Clock pin means connecting to this, right? As I show you here, you see that 8 megahertz, right? And then you can do whatever you want. So you don't need clock generated because the clock is generated already on CPLD board, development board. But for the TTL IC, if you want to go for this one, you need clock generation, okay? And let me spend 5 minutes to talk about this, okay? 5 minutes, 7 minutes, all right? So we have, this is important. Let's say, by the way, you need two things, okay? Let's talk about first, before clock generation, talk about 5 volts. How you gonna get the 5 volt power supply? Because you are going to make this project, okay? The one option is that you say, I know that my, so let's talk about 5 volt, okay? options that you have 5 volts. One is that you say, hey, you know, we have a device called ETS. You remember that red device, 7000? That one, actually, the one that we design our circuits, right? The red one, the digital trainer. That one has a 5 volt, output. You can use that one, no problem, okay? But you say, oh, you know, I want to be a little bit more creative. I want to learn a little bit more. So can I go for other options? The answer is yes, okay? You can use voltage regulator. And this is the road that I went because that time I was very curious about how things work and I wanted to learn things, right? So voltage regulator, what is it? First, you have AC, okay, 220 volt. You can actually have access anywhere, okay, in the country, in Thailand, that has a power outlet. You can get access to this one. Am I correct? So now you have to convert this to DC. You learn how to do this. DC, AC to DC, let's say to DC 12 volt. Okay. From 220 volt AC to 12 volt DC. Okay. So AC to DC converter schematic. Okay. So here it is. So simple. Continue this. So that's the circuit, right? So here you have your DC, and then here you have 4 diodes, right? Can you see the diodes? We call it bridge rectifier, okay? 4 diodes connected this way. Now they teach you actually the theory of this in electronic devices, if I'm not mistaken, when they teach you the diode. And here the output is actually, the output is now DC. So you have to buy 4 diodes. The diodes, so I don't want to read all this, but can you see we even have the diode number 1N4007. It's a little bit thick, okay? Why is it thick? Because you connect it to 220 volt, okay? It's very big. The diode is big, okay? So you put it like this. Then here we call this a smoothing capacitor or iron capacitor. Why? Because the output, when I look at the output here, right, becomes like this. The output is like this. It repels because of the rectifiers. Then you want to make it smooth like this. And that's the job of that capacitor, this capacitor, okay? So 4 diode, 1 capacitor, and this is what we call the voltage regulator, okay? Now, as you see here, for example, the DC is 25 volt or 20 volt, or depends on your circuit, how you design things, okay? Then this is actually, for example, transformer, okay? The transformer 230 volt to 13 volt, okay? So the 20 volt, you need to have a so I don't show the schematic here, a schematic, right? You can find it online. You need a transformer, 4 diodes, and a capacitor, okay? And this is voltage regulator that I say is here, okay? I will talk about that. That's important, okay? So anyway, somehow after the transformer and rectifier diodes, you will have DC, okay? But that DC is, let's say, 12 volt, sometimes 15, depends on your transformer, okay? 15 volts. Sometimes in this case is how much? Let me see. In this case is 13. Can you see? It's 25 volts. No, this is for the cap. It's 13 volt, I think, if I'm not mistaken. Okay, go and read. Yeah, 13 volt here. Can you see? 13 volt AC, but this is AC. It becomes how much DC? Does it say? Let me search for the DC. DC. 12 volt. Okay, 12 volt. In this circuit, right? That this one show based on the transformer and the components they have, they could convert 220 volt AC to. So let me give you this URL. Okay. There are many articles like this online. Let me go. Where is my class? Yeah. Okay. So here it is. That's you can actually AC to DC converter circuit. You can actually go and find a lot of articles online. But anyway, come back here. Somehow you connect this. In this case that I show you is 12 volt DC. Okay. Now, can we use 12 volt for our digital circuit TTL ICs? The answer is no. What's the voltage that we need? 5 volt. We need 5 volt. So here you have to again downgrade the 12 volt to 5 volt. Okay, and that's actually the job of voltage regulator. So voltage, I'm gonna give you the voltage regulator. Google voltage regulator 7805. That's actually the IC that you have to buy. Okay, 7805. So I'm gonna put this is a key IC, so I'm gonna put this one also in the chat room so you will not forget. So this IC, as you see, is look like this. Okay, look like this. Okay, it has 1, 2, 3 pins, and can you see the IC has a hole? Is connected to a metal and a hole. What is that one? That one is actually because if you study this IC, you will see that it dissipates a lot of heat in some circumstances if the current is high. Okay, so this IC becomes very hot when it's working, when it's under load, and then you have to come up with a means of reducing the heat or dissipating the heat, and that's actually done using what we call a heat sink. Am I online? Hello?
Huh? Yeah.
Oh, okay. Okay. Heat sink. Okay, heat sink. Okay, here it is. So, okay, so when you buy this IC, you have to buy this metal too. Okay, it's called a heat sink, and you just connect it with a screw and nut to this IC to the back. Here we have a good example. You see how people connect it together. Can you see that? Okay, and you can buy all of this online in those websites that I have already talked about. You remember the ES, this one, the es.co.th. This website has it, this one. So 7805, you just go there, search for 7805 power supply, probably. No, not power supply, this one. Yes, here, regulator, linear regulator, okay. Let me see how much is it. It's very 15 baht, it's very cheap. You have to buy this one, 8 baht, okay. 8 baht, and then 8 baht is that one, heat sink regulator. Let me see if I can find heat sink. Heat sink. Heat sink. Why this one? Yeah, heat sinks. Okay. All right. Here, here. Yeah, this one. Okay. How much is it? This one is also 8 baht. So total is 16 baht. And then you can have a voltage regulator. What it does, it reduces the 12 volt to 5 volt. Okay, let me show you the circuit that how to connect this. Okay. So new tab 7805, and you can go to images and see the schematic. Here it is. Here it is. So this IC has 3 pins. One is input, another is output, another is ground. Simple as that. Simple as that. So let's go here. I'm gonna show it here. Here. So from AC to 220 volt, you get to 12 volt. But in order to convert it, right, you put that IC like this. So here you have 12 volt. This is IC, let me use another color, 7805. Okay. Then you have an output. This is 5 volt. And then this is ground. Now this ground is common, means now this is GND ground, and this one is also GND. Okay, think about it like this. So can you see I can easily reduce the voltage level from 12, from any voltage to 5 volt, and that's why this is 7805. Now if I want to the output to be 6 volt, actually we have another IC 7806. If I want the output to be 12 volt, we have 7812. We have 7809. So this part, right, is the output voltage. We have many versions. It's whatever that you want, you just buy that IC. For the digital circuit, we want 5 volts, so we need this regulator. But look, here the voltage is dropped, okay? The voltage is dropped. But the current, what happens to the current that goes through this? The current, okay? I, that goes through this device. Look, we have the, you remember the power formula? Power is voltage times current, okay? Now, if before we have 12 volt, okay? Before here, we have 12 volt, but here we have 5 volt, okay? So let's say the current is 1 amp. 1 amp, okay? If we have 12 volt, what's the power at this side? What's the power? 12 times 1 equals to 12 watts. But here we reduce the voltage to 5 volt. 5 times 1 becomes 5 watts. So here you have 12 watt, this side, 12 watt. The other side, how much wattage you have? 5 watt. What's the difference? 7 watts, right? 7 watt is gone. Gone to where? Can someone tell me?
Heat.
Heat. Who said heat? Who said heat?
Siri.
Pong Siri, come on, you answering all my question. Pong Siri, next session when you come to class, okay? I think I remember you. Just tell me I'm Pong Siri. I want to know your face, okay? Who is Pong Siri? Pong Siri. Are you the student in the middle? Second row middle?
No. I'm
no,
the last
first
row.
one. First row middle, right?
No, I'm
Where do you
first
see it?
row, last
one?
last row, yeah.
Last row. Oh, you are coupled with the lady, right? At the end on the right side?
Yeah.
Okay,
right.
okay, now I remember. Okay. Okay, now I remember. Yeah, you're good actually. Yes. This 7 watt has to somehow, because nothing vanishes, right? It actually becomes heat. Your friend Pangsiri is right, becomes heat. Okay, so now you understand. If you understand this, right, you understand why we need heat sink, the way that they show you, right? Heat sink, and why this thing has a hole to attach the heat sink, because this thing, believe me, you cannot even touch your finger when it's working, right? It becomes so hot. If you touch your finger will burn. Okay, the temperature is very high. That's why sometimes it's go to 80 degree, 100 degrees Celsius. It's like you touching the boiling water. Okay. Yeah. So if you understand this, now back to here. When you want to pick your transformer, right? From 220 volt, this is to 12 volt, okay? You have to be careful because we have sometimes transformers that they step down the voltage, but it's not 12, let's say it's 15. Now, if you choose 15, my point is this, if the input is higher, let's say 15, now the wattage that has to be transferred to heat increases. Now here, instead of 15 minus 5 is 10. Now 10 watts have to be dissipated. So the input is always better to be closer to the output. This is called a voltage regulator. Why regulator? Because it regulates the voltage. Means here, whatever variation of voltage that you have as the input will have no impact on the output. The output will be 5 volt, constant 5 volt. That's the meaning of regulation, regulator, okay? Means the input, a change in input will not have any effect on the output of this device, okay? But that's why we can use this for voltage, for bringing 12 volt down to 5 volt, okay? But don't put high voltage as the input. Why? Because then you will have a lot of heat generated. Now that you know this thing, right? So what's the third option? So the first one, you come to the lab, you get the ETS. The second one is voltage regulated. There is another one, the third option. Now that you know this circuit, you actually can go to 7-Eleven and buy a 9-volt battery, okay, like this. Every 7-Eleven in Thailand, they have this, okay? It's just 9-volt battery, okay? So now that you know the circuit, right? This is your battery, 9 volts. This is the plus, and this is minus. And then the only thing that you have to do is to buy that IC that I show you, 7805, right? And this become ground, and this is 9 volt. And this become how much? 5 volt.
5.
Yes. And this is ground. That's it. So and now you have 5 volt. You can apply this to this is now your DLD project. Okay. Now let's talk about clock generator. How are you gonna generate clock? Okay. How are you gonna generate clock? The first is RC oscillator. Okay. RC oscillator. This is actually I not related to our lab, but I like to talk about these things. Okay. So you can actually do your project. Okay. I don't want to make it difficult, so just here is the formula. Here there are a lot of theory that tells you why it's like this, okay? But here is the formula, okay? RC oscillator example number 1. And this is the frequency that you can have if you set the proper values for resistor and capacitor. So basically, let me show you. Yes, something like this. It's simple. It's actually very funny. A lot of students they think is not possible, but it's possible. We have something called RC oscillator, a very simple capacitor. Can you see the capacitor? and resistor, right, can generate, you just need to use these two components, generate oscillation. It's not very accurate, but it's accurate enough, okay? So one is just to use a RC oscillator, okay, to create 1 hertz. 1 hertz, you need 1 hertz, okay? And just Google RC oscillator, 1 hertz means resistor, capacitor combined together, you can do that. Another one is called Schmitt trigger oscillator. Schmitt trigger, just this one is actually the good one. I suggest you go for this because it's accurate and you can use the TTL IC, okay, inverter IC to generate this. How? I'm gonna show you. So Schmitt trigger oscillator, okay, it just that's actually the circuit. It only needs a simple inverter. Can you see the inverter? But this inverter is a special one. It's Schmitt trigger inverter, okay, and a capacitor and a resistor. Only 1, 2, 3 components, okay. Then here you will have a clock coming out of this, okay. So let me show you one good one that you can actually follow. Yes, this is, so I'm going to give you this link. Later on, you go and study this by yourself, okay? So you see, based on the R value of R and C, you can change the frequency. Here, actually, you can do the simulation. What's the value of R? 1K, 2K, whatever that you want, you can put here and simulate. And finally, you have to tune this R and C so you can get 1 hertz, okay? Now notice, what's the IC number for this inverter? 7414, okay? So 7414 is actually an inverter, but a special inverter of type Schmitt trigger, okay? So you just need to buy 1 resistor, 1 capacitor, and 1 IC 74. This is actually TTL IC 7414. And then you can generate here, generates 240 hertz, and then it uses clock divider. Can you see this? This is a clock divider to divide it by 4 and get 60 hertz. But you actually can generate 1 hertz, believe me. You don't need to go high 240 hertz, okay? If you change the R and C, you can generate directly 1 hertz. And finally, find the final, this one actually is the one that computers use. If you have a computer, right, you have like 1 gigahertz clock, 2 gigahertz clock running, right? They use crystal oscillator. Okay, so you can actually buy this. This one, you can use this too, but okay. So the schematic. This is actually the way that the CPLD development board uses here, but it's a little bit difficult. So let's go to image. Yes, it's like this. Not difficult, but so you have to buy a crystal, okay, and then here you have to buy two capacitors and 1 resistor, and then you will, here the output will be the frequency that you want, okay? So crystal oscillator is another option. Now this is not related to our course. I only explain because I want to help you to come up with, then you want to do your project, right? So now you know how to generate the 5 volt and how to generate clock. Is there any student who have any question regarding these topics? Questions? Okay, good. So now that you know how to generate clock, let's go and see how we can use this clock efficiently, okay? All right. In order to create sequential circuits. This is a clock, right? All So now we learn that we have CL circuit, we have sequential circuit. The sequential one, the ones that have clock, we call them synchronous, okay? And we use them when we want to do something that happens periodically according to the arrival of clock edges. And what else? And that's it, okay? And then we also need to have memory, okay? Sequential circuits, they need memory. Now the question is this: how can we make memory in digital circuits? Okay. The answer is this: flip-flop. The storage elements or memory used in clock sequential circuits are called flip-flops. A flip-flop is a binary storage device capable of storing. This is important. How many bits? Only 1 bit. A flip-flop can store either the value 0 or 1. That's it. Only 1 bit. Okay. Latch. There is another term called latch. This is also memory storage elements that operate with signal levels rather than signal transitions, are referred to as latches. Okay. So here we have the concept of memory. In digital circuits, we have 2 types of memory. One is called flip-flop, another is called latch. So here it says latches are sensitive to signal level. So here I say level. Maybe I use another color. Color is better. Green. So level. Okay, they are sensitive to level, but flip-flops are sensitive to what we say age of the signal. Sensitive to the age. Okay, you will see what it means later. Don't worry. Latches are said to be level sensitive devices. Flip-flops are age sensitive devices. So that's why here I write age, here I write level. Latches are basic circuits from which all flip-flops are constructed. We will briefly look at many different kinds of latches. Okay, so the first thing that I'm going to look into is the latch, is this one. Okay, is the latch, which is level sensitive. Now, if you have 2 NOR gates like this, 1 and 2, and connect them the way that I show you here. Okay, now this is actually very strange way because the output of this is connected to the input of the other one. Then you will have a memory. This is memory. Okay, now a lot of people don't understand why this is a memory. Okay, now pay attention, this is very important. Okay, I'm gonna show you why this is a memory. Let's say I want to store information in digital circuits, okay? That's my goal. I want to store information. I want to create a memory. And this is the way that actually I can do. I can have an inverter and I connect it to another inverter, okay? And then I connect the output of the second inverter to the input of the first one. Can you see this? So here, let's say if I have 0 here, the 0 will be inverted, it becomes 1. The 1 will be inverted, it becomes 0, and the 0 will reinforce this 0, and here it keeps going like this. So let's say if I look at this as the output of this memory, then I can say, hey, you know, this memory actually holding the value 0. Right? So I can say that this is a memory. Am I correct? As long as the power is applied. The power, this is, you remember the VCC and ground, right? We have to have for the inverter, right? But we usually don't show it. Don't show it on the schematic. So as long as I have power maintained, then this circuit will keep the value 1 for me. Am I correct? Somebody say yes. Okay. Now the question is this: how can I change the value of this memory? Means if I want to, as instead of 0, right? Instead of 0, I want to store 1. How can I do that? Okay. Now, if you pay attention, I can somehow magically inject the value 1 here. Think about it like magic. Okay, some magic must happen. If this become 1, this becomes 0, and this become 1, and the 1 comes here again, and then I store the 1, right? How can I inject this? I'm gonna give you 3 points. If a student tell me, how can I inject this 1 into that wire? I want to inject 1 into this wire. How can I do that? How can I do that? Anyone? Anyone? Look at this. Look at this. Look at this carefully, okay? If I put a, where is my, let's say this one, okay? If I put an AND gate or OR gate, it doesn't matter, or XOR gate or NOR gate or NAND gate, doesn't matter, okay? Let's say or NOR gate. That's a simple one, AND gate. If I put an AND gate, okay, and like this and like this, and now this is actually that injection. Okay, so here, let's say initially, let's get rid of these numbers. Okay, so if I put here 0, it doesn't matter what is this one. Okay, this becomes 0, 1, 0. So by putting here 0 and the 0 comes here. Okay, then if I change this to 1, it does not propagate. So actually AND doesn't work. Let's switch to OR gate. Okay, so the OR gate, right? The OR gate. If you see now I'm experimenting, right? Experimenting. I want to inject a value there. So let's get rid of this. OR gate, I put here 1. Okay, I put here 1, and it doesn't matter what to be here. This becomes 1, this becomes 0, this becomes 1. Okay, and the 1 comes here, and then if I put this here 0, the 1 here will not let this to be affected, so I cannot change it, right? So and OR cannot be used for that injection. Can you see that? Okay, but let's say if I put XOR, now you have to see the XOR table. Delete this and gone. XOR. So this is XOR. Now look at the XOR. XOR I can, if they are the same, okay, look at this. If they are A and B are the same, you will get 0. Okay, if they are different, you will get 1. Okay, so if I here, now this is, let's say this is XOR. Then, so let's get rid of this. Okay, so this becomes that injection, and let's say this is XOR. Let's see if it works or not. Okay, so let's say I want to put 0 here. I go here 0. If I put here 0, okay, and this is 0, 0, 0 gives us 0. This becomes 1. This becomes 0. So I can store the 0. Okay, then the 0 comes here. Now, how can I make this to be 1? How can I make this to be 1? I only need to make this to be 1, and this becomes 1, and 1 becomes 0, and 0 becomes 1. You got the idea? Can you get the idea? You see, you have to find a way of injecting. Okay. Now, this very simple idea is actually what the fundamental of memory. Okay. Now look at this. Actually, even if you don't have the injection, this is called the memory. Okay. Now look at this. Look at this. These two inverter, right, that I just drew like this, right? I'm gonna put this one in parallel with the previous one. So I will have something like this. Okay, so if I move this to here, right? Move this to here, this thing will come here, right? I'm moving this. Can you imagine this? I'm moving this to here. So instead of this inverter to be here, I move it to here, okay? So the wire becomes like this. And this one, the output of this, right, is connected to the other one. I can actually do it like this, right? Is this the same, right? But that's what people do. They don't do like this. They do like this, okay? Can you see the cross? Can you see this cross? Can you see there's a cross? Actually, this is the thing that is make the student confused. If I show you the schematic like this, you will not confuse. But if I show you that like this, you will get confused, right? But that's actually now because I show the schematic like this, it's better for you to visualize things, right? Now look at this. Can you see this cross? Can you see that? So what's going on here? Here, the people, they say, instead of that injection idea, we are going to replace this with a NOR gate. Instead of inverter is NOR gate. So it can have two pins like this. And then according, this is called S, this is called R. According to the value of the S and R, I can actually set the output of this memory output. Does it make sense? So if you do this, this is actually memory, okay? Now, if you get confused why there is a cross here, it's just look at this, okay? Rewatch what I just explained, okay? This is actually this one, but so this thing is this, is exactly this. But I move this NOR gate down. Instead of put the NOR gate here, right? I move it down here. All right, now look at the behavior of the table. If I want to have 1 saved into the memory, the Q is the output, okay? Then what I need to do, I have to set, because I want to have 1, I have to set. Means I put here 1, I put here 0, set the memory. Now the memory will retain the value 1. Now after I set, if I put this change the set to 0, what happens? Nothing. So it will remain as 1. Then when I want to reset, I put this one to 1 and this one to 0. So the memory becomes 0. Now if I set this back to 0, 0, 0, right? You see 0, 0. Look at this. 0, 0, 0, 0 will do nothing. You see, the previous, what's the previous value? This one will exactly be the same. You see, these two are the same, right? These two are the same. So for the set, I only need to do this. Set 1, 0. For the reset, 0, 1. This is set. This is reset. Okay, and what happens if I invoke the set at reset at the same time? This is no. This is forbidden. You cannot do this. Forbidden. Okay, now putting these NOR gates together has a name. We call it SR latch, set reset latch with NOR gates. I can repeat this, the same idea with NAND gate. We call it SR latch with NAND gate. Exact same thing. Okay. Now, next level is that I say, I want to have some enable pin. So the input cannot go directly to the memory. And I do that by putting, so what is, I'm gonna encircle this one. Can you tell me what is this one? What is this circuit now? Yes, this is SR latch. This is SR latch. Okay, just next to SR latch, you add two more. Who answered this question? Who was that? I heard the voice of one student. Pongseri again. Pongseri, you got, man, you're gonna, I think only this session, your score, your final score upgraded by one letter. Instead of, let's say, A minus, you will get A. Only because of this session. Okay, so I just need to add this, okay, to NAND gates in order to have enable pin. Now look, what happens if the EN enable pin is 0? We know that 0 comes here. Every AND gate that has one of its input 0, the output will be 0. But this is NAND, so here the output will be 1 automatically. Okay, so if this becomes 1 and 1, and 1 and 1 means no change. No change. Why? Look at this. 1 and 1. No change. Okay. So if EN is 0, the memory has no change. Means the memory will become inactive. But if EN is 1, okay, then S and R can actually propagate, can go inside. And here we again have that forbidden situation, right? So this circuit that you see is called SR latch with EN pin. Now, what is a D latch? D latch. Now look, that forbidden state when you cannot let set and reset to happen at the same time, right? We don't like it. We don't want the set and reset is forbidden, is indeterminate, okay? You cannot tell to someone, sit down and stand up at the same time. You cannot tell to a memory, store 0 and store 1 at the same time, right? You cannot do that. So we want to get rid of it. And that's how we get rid of it. This is the SR latch. This is SR latch. This is the enable pin. Okay, same as what I explained. Now, instead of having SR, this is actually S, this is R. I'm going to get the R from S and invert it. So when the S is 0, the R will be 1, no matter what. When the S is 1, the R will be 0, no matter what. And by doing so, I eliminate the rows that S and R are the same. This will be gone. This will be gone. So when this is gone, so let me use another color. So the S and R cannot be same, right? So I eliminate. This one cannot be the same. I eliminate. By doing so, I eliminate the indeterminate state. And I'm left with only 1, 2, 3. 1, 2, 3. And we call this a D latch. So let's go up here. Let me get rid of this. Okay. So far, what did we learn? We learned latch. We learned what is SR latch. We learned what is SR with EN pin. We learned the D latch, type D. Okay, let's go down. Now, if I want to show SR latch, instead of showing those AND gates, NAND gates, NOR gates, I can actually, this is the graphic symbol of SR latch. This one is the same thing. This one is the NOR one. This one is with the NAND one. Okay, so that's why you have the bubbles. And this one is the D latch with the enable. Okay. Now, next is age triggered D flip flop. You remember we mentioned that flip flops are sensitive to age while latches are sensitive to level. Now, when you look at these truth tables, it's either 1 or 0, and the output is set, the output of the memory. We don't care about the age, it's just the level. 0, 1, 0, 1, right? That's why we say latches are sensitive to level. But what do we mean when we say we have something else that is sensitive to age, not level? What do I really mean? Okay, let's go and find out. So I discussed what is a D latch, right? D latch. Is there any student here who doesn't understand D latch? I think it's just go up here to review, okay? You see D latch, D latch, D latch, where is D latch? Here, this is a D latch, okay? D latch. How many gates do I need? 1, 2, 3, 4, 5. 5 gates, okay? Now I'm going to create a flip flop using that D latch that I just showed you, okay? So you see, I put a D latch here, so 5 gates are inside here, okay? 5 gates are here, 5 gates here, plus 1 gate here, 11 gates. So a D flip flop needs 11 gates, it's bigger than latch, okay? So I put it here. Now what happens is this. Now I have the enable pin. Can you see the enable pin? But this enable pin, now don't think that this is clock. Don't worry about this, okay? Both of them are connected to one source, but there is an inverter in between. So when here is 0, this one is 1 because of this inverter. When this one is enabled, this one is disabled, right? Now look at this. By doing so, when, let's say initially, okay, initially I put here 1. So this is enabled. So the value of D can go here, can go inside and appear here, okay? But then if I change this to 0, okay, then this, the first one will be deactivated, and this one will be active. And what this one is a memory. We learned that D latch is a memory. So the value of D that is gone inside actually is here. This D, okay, is here. And when I activate the second D latch, this will come here. All right. Now, if you look at this transition, right, this is, if I apply this to a clock with this kind of transition that goes becomes 0, 1, you see, 0, 1, right? You will see, okay, you have to read this paragraph, that the moment, on the moment that 1 becomes 0, okay, you see, 1 becomes 0, 0 means this is deactivated and this one is activated, okay? This thing will go inside to the output. So this device is sensitive only to the ages, in this case to the negative age, from 1 to 0, okay? Sensitive to age. So when it's one, okay, it samples the input. This is the D, okay? samples the input. When it becomes 0, it actually put that sample value into effect, into the output. And I know it's a little bit difficult to understand it maybe at first, okay? So you have to read this paragraph, okay? That basically at any given moment, because of this inverter, one of them is activated, right? If this is active, it samples, it brings it inside. Then when the 1 becomes 0, when the 1, only at that time, the moment that the 1 becomes 0, this becomes deactivated and this becomes active, and this actually goes here. So this is the behavior of what a device, we call this master slave, D flip-flop, that is sensitive to age. Now I just show you, right? It's sensitive to age. And the age here is the transition of 1 down to 1 down to 0. Can you see that? 1 down to 0. And that's why we say flip-flops are age triggered. Okay. Now let's go up here. So I just show you what is it. That thing is again back. So here we have SR latch. Sad. So hold on. Let me where is my, okay, let me get rid of this again. I press Ctrl Z and all these things come again. Oh. Okay, so let's categorize them again. So latch is sensitive to level. We learned the SR with enable pin, and D latch. Now we learn a new type of flip-flop that is sensitive to age called D flip-flop. Okay, D flip-flop. Now let's go down. Now D flip-flop, okay, can only perform 2 things. Now look at this. This is the D. Okay, you can only set the D to 0 or 1. That's it. Okay. And or in other words, you can set or reset. Okay. But sometimes you want to give more commands to the flip-flop. For example, in the case of D flip-flop, right, we have set, reset, or D is 1 or 0. But sometimes I want to have another command. Let's say toggle. What is this toggle command? Toggle means, oh, I don't want to tell you to hold the value 0 or hold the value 1. I want to tell you whatever value that you're holding, invert it, toggle it. If you are holding 0, now please hold the 1. If you are holding 1, now please hold the 0. That's the meaning of toggle, okay? And that's a command. Now, if I have 1, set, reset, and toggle, how many bits do I need to have 3 commands? Actually, 2 bits. 2 to the power of is 4, okay? So I say, oh, you know, for the set, if I tell you 0, 0 means set. For the reset, I tell the flip-flop 0, 1. That's the command. Toggle, I say 1, 0. And 1, 1 is not used, okay? Not used. Now, as you see, I need to have 2 bits. And that's actually JK flip-flop. J and K are the input, okay, that you can set, reset, and toggle. D flip-flop cannot have it, okay? But I don't, it's out of the scope of the lab. This is lab, okay? This is not lecture note. So let's go here. Where is my, so I don't have the JK schematic here. Where is my, oh, here. So now you learn that there is another kind of flip-flop called JK. Okay, JK is here. Okay, now Sometimes you don't care about setting and resetting. What you care is that what you want is just, so here, that's what I'm explaining, is just to reset the flip-flop, means initially is 0. And then you just need to tell the flip-flop to toggle. So when it's 0, it becomes 1. When it's 1, it becomes 0. When it's 1, it becomes 0. And then you can actually toggle the flip-flop or toggle the memory. And that's another kind of memory that you can only tell to the memory to toggle, and we call it a T flip-flop. Now, why do we use this? Because as you see, the T flip-flop is very simple. It can only toggle, right? For a D flip-flop, how many gates I need? I need 11 gates, right? But let's say for the T flip-flop, you can have 9 gates. So 2, 3 gates less, okay? So it's like a little bit smaller if I go for T flip-flop. So here we have another type of flip-flop, T, and that's it. Now, you know, or actually very advanced. This is the thing that I showed you, right? Is very advanced memory theory in digital circuit. You know everything about memory elements, okay? Not everything, but all, like latch, you know the latch, you know the flip-flop. You know that we have SR latch, D latch, we have D flip-flop, JK flip-flop, and T flip-flop, okay? Now, can we have a break? Because right now, after that, not the concept of sequential circuit is over, and I'm going to discuss a state equation. Actually, this I'm afraid that maybe takes like 40, 50 takes a while. Yeah, takes long time. I have to go a little bit faster. Let's have a break for 5 minutes, 7 minutes. Okay, what time is it? 11:10. Let's come back 11:16. 5 or 6 minutes. Maybe I'll come earlier. Okay. See you.
Okay,
A little bit of break. I make coffee. Okay. Okay. Okay, we are back. Okay, so let's continue. What is this? All right. So now that we know how to create memories, that topic is over. We are entering a new topic, okay, which is related or uses the memories, all right? And that's the sequential circuits. The first topic regarding sequential circuits is a state equation. What is it? It specifies the next state as a function of the present and inputs in algebraic form, okay? So look at, you remember the counter 0, 1, 2, 3, 4, right? So basically you can come up with a circuit that says, hey, what's the input? If the input is 0, okay, and what, no, sorry. Yeah, here actually doesn't have an input, okay? So this one doesn't have input, but some other circuits have, all right? So what's the current state? 0. Based on the current state, and let's say input is, let's say you have a plus x, okay? If the x is 1, then what's the next state? The next state is 1. Current state is 1, input is 1. What's the next state? 2. Now, if you change the input x to, let's say 5, current state is 2, input is 5. What's the next state? 7. You jump to 7. You see? So the present state and the input can actually form the output. Now, how to do this? You actually do this via, or define this via a state equation, okay? Take a circuit shown in figure 110, this one, as an example. For now, we are not concerned about what this circuit does, the functionality of this. We see only it has 2 flip-flops, 2 memory. You see D flip-flop. It has 2 memory elements. Each one of them can store either 0 or 1, 0 or 1, okay? So how many bits I can store in this circuit? 4 bits, only 4 bits. Sorry, 2 bits, but 4 combination. Okay. Now, if I give you this circuit, and the moment, exactly the moment that you see that, oh, this circuit has D flip-flop, means this one, right? Means this circuit has memory, means this circuit is sequential circuit, synchronous circuit. Why? Because it has a clock. Can you see the D flip-flop? It has a clock. That triangle, okay, is a pin that you shall connect to clock. Okay, so this is a sequential circuit. And then we say, okay, tell me what it does. I want to know what this circuit does. Then what you should do is to look at the input here to the D flip-flops and write the equation of the input. So if I look at this, I say, hey, a t plus 1. If at any given moment time t, okay, at is the input. When clock comes like this, when clock comes, right, then at means the value of the value of the next how to say this? So basically, let me do like this. The value that is generated here, okay, generated at this location using these gates, right? At the time of arrival of the clock, which, because this is D flip-flop, so you have to pay attention to the age. At the time of, for example, this time, you have a rise in age, then this value will go inside the flip-flop and can be shown or propped or pasted here, okay? So this thing, when the clock comes, go here, okay? So AT means the current value of A. Okay, AT plus plus means the next state or next value of A. A is a memory. This is A, memory A. Okay, this is memory B or flip-flop A, flip-flop B. Okay, so the next value. So this becomes the next value or next state, the input, next state, or A, T plus 1 is here actually. No, this is B. B T plus 1. T plus 1. The next state or value of the B that will actually become the current value of the B. Okay. The next value of the A that will become the current value of the A. What is AT plus 1? You just look at this thing, okay? So AT plus 1 is the next value, right? Now, ATXT. Look at this. This is AT, right? AT comes here. XXT. Current value of A, current value of X, and together. Here it is, and together. And then there is an OR gate. Then the current value of X and the current value of what? What is this? B. Current value of X and current value of B, or together will generate the next state of A. Okay. So you write the equation like this. Now, if I want to write the state equation for the flip-flop B, this is, I look at this point. This is going to be the next value of the B that will actually, when the clock comes, will replace the current value. It goes here, okay? So what is it? It's the end of this one. What is this one? A bar, A bar. So here I have A bar and X, and together. And then your circuit might have an output. This is the output. Now, as you see, the output is not coming from the flip-flops, okay? So whatever the equation is, you just look at this one. What is this one? This is B, this one is A, and this one is X bar, right? So I can say Y is A or B and with X bar. A and A or B and with X bar, okay? Now, look, if I, AT means, AT means, I write this, okay? So you will not confuse current value of flip-flop A. AT plus 1, next, gone. Next, can I redo? Cannot. Next value of flip-flop A. That's why we put AT plus 1, means next value. AT means current value. AT means current value. Current state. Or states, okay? So if you, this is what you see here is called a state equation, okay? But if we use these parentheses and T's and T plus 1, it becomes very complex when the equation is complex. So we just drop them, okay? We're removing the T. For example, YT becomes this. This one, okay, becomes this. Remove, you see, I remove the T. Can you see? And this is called the state equation. Now, me personally, I don't even use this one. I use NA. I say NA, next value of A is AX plus BX. NB, next value of the B. So if you ask someone, hey, what does this circuit do? Then the engineer says, okay, it does this. It just gives you these equations, okay? The state equation of the flip-flop. All right. Now, a state table is the same thing. If you have the state equation, you can write the state table same as the CL circuits. If you have the schematic, you can come up with the equation. You can then draw the truth table, right? Here is the same thing. But now here, we have current state or value and next state, input and output. Okay. So if you want to draw the truth table, a state table for this circuit, okay, first we get the equations, the state equations, then we draw a table like this. And then we say how many input we have? How many flip-flops we have? 2 flip-flop A and B. So we can actually have 4 states. How many input we have? 1. That's the input. So you list all the flip-flops and all the inputs. And then you say, okay, right now I'm at state 0, 0. The input is X. What should be the next state? Okay, so now here, next state of what? A. What's the equation A? AX plus BX. So I have this equation. This is called the state equation. NA, next state of A is AX plus BX. How did I get this? Just from the schematic, okay? You see, it's nothing fancy. It's just AX, right? This is BX. That's it, okay? And this is NA. And this is A, okay? So I say, hey, I have this equation. What happens if A is 0, B is 0, and X is also 0? Just calculate, okay? Just plug the numbers, 0 and 0, 0, or 0, so NA is 0. That's why here you have 0, okay? What is the next NB, next B? I have the equation here, NB is A bar X, A bar X. So next state of X when X is 0, A is 0 is 0. That's why here is 0. And you can do the same thing for output. Y is, what's the Y? Y is A or B X bar. And then you see, A, B, and input, right? Three variables. So you will have 8 rows. Why? Because 2 to the power of 3 is 8. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, all the way to 1, 1, 1. And then you plug the values here into the equation and you can get the next state and output. And if you do that and you write a table like this, then you actually written or completed the state table. We call this a state table, all right? Now, a state table has another form too. Now, in this form, as you see, I say, okay, I have 2 flip-flops, and every flip-flop can have I have 2 flip-flops, 2 to the power of 2 is 4. So I have 4 states, and these are the states, A, B, 0, 0, 0, 1, 1, 0, 1, 1, okay? And then I ask myself, if I am in the state 0, 0, what will be the next state when the input is 0? What will be the next state when the input is 1? Basically, this table is exactly the same, except that I put the inputs on top of the state, okay? You see, the input is on top of the state. So this version has less rows, okay, and is a little bit easier to read. So you can see, for example, if you're in a state 1, 0, it goes to a state 0, 0 when the input is 0. It goes to a state 1, 0 when the input is 1, and so on. Okay, now a state diagram is the same thing. If you have the state table, you see, from 0, 0, it goes to 0, 0 when the X is 0. So here I say, when you want to draw this, you first have to know how many flip-flops you have. In this case, I have 2. Then 2 to the power of 2 is 4. So I have 4 states, state 0, 0, 1, 0, 0, 1, 1, 1. And you just draw them, okay? And then you have to look at the state table. You say, hey, if I am in a state 0, 0, this is the initial state, 0, 0. Okay, here state 0, 0. Then if the input is 0, what will be the next state? Here, this is the input, X. Okay, so basically, can you see there is a number with a separated, two numbers separated by a slash on top of each arrow. Okay, here the number is like this form of input output. So X is input, output is that Y, the output of the circuit. So when I am in a state 0, 0, I go to a state 0, 0, means to myself when the X is 1. Why? That because the state table says, you see, from 0, 0, I go to 0, 0 when the input is 0. But what happens when the input is 1? I go to what state? 0, 1, right? Let me have coffee. Right? 0, 1. I give you another example. Let's say we are in the state 1, 1, means here 1, 1. Okay. What happens if the input is 0? Input is 0. I go to a state 0, 0. If the input is 1, I go to a state 1, 0, but the output is 0. Okay, or output is 1. So let's look at this. 1, 1. Input is 1. You see, input is 1. I go to 1, 0. Can you see? I go to 1, 0 when the X is 1. So from here, I go to 1, 0 when the X is 1. Okay, and you draw this, and this becomes from the state table, you draw the state diagram. And now if I ask you, hey, can you tell me what that circuit does? Actually, it becomes a little bit easier. Okay, if you spend time on this, all right, you can actually figure that out. The answer is this, that this circuit that you see up here, right? If I tell you, hey, tell me what it does, you have no clue. But after you get the state table, first a state equation, then a state table, then a state diagram. Now, if you look at this, it's kind of like, wow. If you think a little bit, right, and track this thing, right? So you will understand that this is actually a zero detector. How is it possible? Look at this. I'm gonna show. So input, what's the input to this circuit? X, right? Now, initially, when the X is 0, then you also have a clock. I'm gonna show you the clock up here. Okay. So this is sequential circuit, so you have clock. Okay, so every time that the clock comes, let's say we are sensitive to rising edge, so I'm gonna put all this rising edge here, like this, sensitive to rising edge of the clock. Okay, every time that the clock comes, the state changes. Okay, initially, let's say I'm in a state 0, 0. Input X is 0. Maybe this color, okay? So this clock comes, okay? I'm in 0, 0. The state is 0, 0. X is 0. What's the next state? 0, okay? And what's the output? This is the Y, the output. Y. The output is 0. It doesn't matter how long the X is 0. 1 year, 2 year, yeah. Y will be 0, okay? Because of this, it just keeps being here. But when the X becomes 1, let's say here the X becomes 1, at this moment, when the clock comes, what happens? The output is 0. So the Y will, now the X is 1, but the Y will be 0, okay? But the state internally changes from 0, 0 to 0, 1. Now here, if the input X is 1, okay? So let's say it keeps being 1 for the next clock cycle. Then you keep changing the state, you go here. Then let's say if it's still 1, like this, then you go to next stage. So how many clock cycle? 1, 2, 3. You see, 1, 2, 1, 2, 3. And then here, the X is 1. So you stay here. It really doesn't matter how long. Forever, you stay here. But the moment that this thing becomes 0, the X becomes 0. Like this, okay? Now, it doesn't matter if you are here when the X is 0, you go to this state. When the X is 0, you go to this state. When you are here, the X is 0, you go to this state. Can you see that? Can you see that? And these 3 arrows are the only arrows that the output is 1, okay? The output is 1. So when you are at this stage, the X becomes 0. Then the output Y becomes 1. Here become 1. It's like a scream. Okay, it becomes 1. And then when you go here, when X is 0, so the output becomes 0. So the output at next clock cycle is 0. Okay. So what happens? Wow. Actually, this circuit, right, looks at the input. This is the input X. Okay. And the input, when it goes high, it notices. Okay. And it waits. When the input is 0, output is high. Can you see that? So basically, it says it's a 0 detector. Okay. Means every time your input goes to 0, this circuit screams. Say, hi, I detected a 0, a transition to 0. And this one, the 0 detector, right, is very actually useful in many circuits, in telecommunication. We use it in telecommunication, okay? But pay attention that we cannot actually have a 0 detector if we don't have memory, because we have to remember what was the previous state of the input. If it's 1 and the next state is 0, you see, can you see that? Is exactly at this location. When here is the input is 1 and here the input becomes 0, then you have to set the output to 1. So now you can see why memory is important, because you hold or save or remember the previous state of the circuit, okay? So now that we know this, let's go and see how we can code this in Verilog, okay, coding. Now, if I want to use TTL IC, I can use the this TTL IC D flip-flop. Okay, I can use here this one. What's the name of it? Name the IC name. Here, 7474. Okay, 7474 is flip-flop. I can just use 7474 to implement this and this. Each IC has only 2 flip-flops, and then other gates as normal, and then I can have this one, okay? But what happens if I want to code? Okay, let's see. The first thing that you have to know is this thing called, we have 2 kinds of assignment, blocking assignment and non-blocking assignment, okay? This is very important, okay? Because we use this in order to create a state, okay? Now look at this 2 statements versus this 2, okay? This is blocking. This is non-blocking. Why? Because here I use equal sign. Here I use less than and equal sign. Okay? So here, equal sign, less than, equal sign. All right? Let's see the difference. It's very important, okay? So let's say I have A, B, C variables, okay? Let's say A is 10, B is 50, C is 30, initial values, okay? Now, what happens when the Verilog compiler comes to execute this? It says put the A to B, right? So what is A? 10. Put it into B. What is B? 50. So B is no 50 no more, and 10, it will be 10. All right. Why is so? Because it's blocking. It says, I'm going to block the execution and you have to do the assignment. Do it now. Do it right now. Like this, okay? And then C, B plus 1. So what is B? B is now 10. 10 plus 1 is 11. And now C becomes 11. Okay? So after executing these two lines, you have 10, 10, 11. Now for the non-blocking, I have the same. So A, B, C. Okay? So A is initially 10, 50, and 30. Same values that I give. Now, I say put the A to B, but it's non-blocking. I say not now. Don't block the execution. Just remember, look at my wording. Just remember means memory, right? Remember that you have to put A into B. So the compiler says, or even humans, they do that. I say, oh, I have to put the B into, put the A into B. So A, what is A? 10. I said, put 10 somewhere. This is like a corner of my I have a piece of paper, and on the corner I just write, right, very small note. Put 10 into B. Put 10 in B. This is like a small note that I have, but this is actually working like a memory. This is a memory, okay? Put 10 into B. Okay. I try to remember it, so this is my actually notes. Then put B plus 1 into C. Okay, what is B plus 1? B is 50 plus 1, 51. So I, again, put 51 into C, in C. Okay, what is this one? This is, again, all memory. Somehow I have to store this information, okay? And why is that? Because now I'm using different symbol. This is non-blocking. Now, when I reach at the end of the block, all these assignments must be done. Now put 10 in B, so this becomes 10. Put 51 in C, this becomes 51. Now notice the difference. 10 here is the same, right? A never changes. B is the same, but the C is not the same. Can you see that? Can you see that? Now I have to teach very fast because I don't have time, okay? But rewatch this and practice this and try to understand fully what is blocking and non-blocking. Now that we know, okay, what is blocking, let's go and see how can we code a flip-flop. This is a D flip-flop, right? That's it. It says, I use behavioral. I say always be sensitive at positive edge of clock. Why? Because this is a clock and positive. And that's actually so simple. Put the next X into X. Okay. If you remember in my state diagram, state schematic, right? I say NA into N, right? So it's next A into A, right? It's the same thing, next X into X. So if you write this code, you will get a D flip-flop in Verilog, okay? And what happens if I use non-blocking? Same, I will get a flip-flop. Now, because of this, students confused, they don't understand the difference between blocking and non-blocking. Why is that? You will see when we go to the next example. Now look at this. Here, I say, let's write something like this. Be sensitive to positive edge of clock. Now here it says put the next X into X. But here, is it blocking or not blocking? One student tell me to see if you are listening.
Non-blocking. I mean blocking.
Blocking. It's blocking. Okay. So it says put the next. Who said blocking? Who talked here? Who?
Hong Siri.
Seri, man. Seri. And let me see the students chat or not, because I told them to chat. No, nobody chats. Okay. All right. So let's back to lecture now. Okay. So here it's blocking. It says stop here. Put the next x into x. Stop here. So here you will get a wire. Next x into x. And then it says put the x into y. And now you reach the end of the block. And then you will have 1D flip-flop. Okay. Next x is connected like nothing. It's just like you put the nexus into x and put the x into y. So basically you put the next x into y, right? But here, look, if I'm using non-blocking, then the compiler comes here and says, okay, when the clock comes, I have to put the next x into x, but not now, not now. So you remember when I say not now, what did I do? I go and I wrote a note. But in circuits, we cannot write notes. What should we do? We have to save this somewhere. And we know that the flip-flops are memory, right? So when you write the code like this, actually next x will be saved into this flip-flop like this. And then x goes to y, but not now, but at the end of the block. So when you reach the end of the block, then everything will be executed at the same time. So you will get 2 flip-flops. All right. Now, why here we had both of this code, blocking, non-blocking, had the same effect? Because we had only one line. Only one line, right? But here we have 2 lines. And when we have 2 lines of Verilog assignment, this is called assignment, right? Then you have to be careful. If you use non-blocking or blocking, there will be a difference. None of them is right, none of them is wrong. Sometimes you want this hardware, you code like this. Sometimes you want a D flip-flop, you code like this. It's up to you, okay? Okay, up to you. But usually, it's very weird if people use non-blocking, right? It's very weird like this. So that's why we usually use non-blocking for flip-flops, because it's so rare to do something like this. Okay, who's gonna connect a wire to another wire, right? So how about D latch and D flip-flops modeling in Verilog? Look at that. For the, this is the D. So if you remember, the latch was sensitive to, tell me, sorry. Latch is sensitive to?
One input. Oh, level.
Man, I'm gonna give this. Is this only this student in this classroom? Sensitive to level, okay? So because it's sensitive to level, right? And this is actually the D latch with enable pin. I just simply write always be sensitive to enable and D. And if they change, right, D goes to Q. Q is the output. Simple as that. And I'm using non-blocking, okay? Now for the flip-flop is sensitive to H, okay? So that's why I have to put the keyboard positive H or negative H, up to you, depends on the circuit, okay? And I just say be sensitive to the positive edge of clock, and then D goes into the Q. This is the assignment. That's it, finished, okay? Now you know all the theory. Now, today we have 2 experiments, okay? The first one, I'm gonna show you how to do it. We are going to design a 2-bit sequential up counter. The next one is exactly the same, okay? But instead of 2-bit is 3-bit. But instead of normal counter is arbitrary counter. I will tell you what is it, okay? I hope I can finish it before 12, okay? Now look, pay attention, I'm gonna do it quickly, okay? Experiment number 2 is this. Design a 2-bit up counter by using TTL D flip-flops. But because we are not in the class, right? So we are not going for this one, okay? Don't, when you want to write the report, don't use TTL, use Verilog. And here I have given you the Verilog code, right? This is the module. So just use this one, okay? All right. So now let's design page style. Fine. Okay. So my experiment number 2 is designing up 2-bit up counter. Means I have to design a circuit that shows 0, 0, 0, 1, 1, 0. 2 is 2-bit, right? 1, 1. Means 0, 1, 2, 3, right? Now I have a question. How many flip-flops do I need?
Two. I think
How many flip-flops?
two
How many
flip-flops.
state I have? 4 states, right? So I can use how many flip-flop?
Two.
Two flip-flop. Okay, 2 flip-flop is enough. Okay, so 1 flip-flop to hold this column, another flip-flop to hold the other column, A, B. That's it. Okay, now I have to write the. You can actually maybe we start from a state diagram. So how many state? 4 state. This is a state 0, 0. This is a state 0, 1. This is a state 1, 0. This is a state 1, 1. So do I have input here? No. So every time that we have a clock, 0, 0 goes to 0, 1. This one goes to here. This one goes to here and then back here. There is no input. If we have input, you should put X, for example, and Y output here. Okay. So if we have input on the arrows, you have to put this in and out. But now we don't have, so that's it. Okay, I have the state diagram. Now I'm going to draw the state table. So I have the state table. This is A, B, current state. Okay, I have 4 states, 0, 0, 0, 1, 1, 0, 1, 1. Then I have the next state, NA, NB. Notice that I don't have input, so I don't put the input. If I have the input, for example, let's say input X, then here I have to actually have another column, okay? But I don't have any. In this example, I don't have any. So NA, NB, next state of A, next state of B. So tell me, when I'm at state 0, 0, what's the next state?
0, 1.
Yes, 0, 1. Is it Pumseri?
Yeah. Me
Okay.
again.
Okay. From 0, 1, I go to 1, 0, right? I go to 1, 0. So the next NA, NB, next state is 1, 0. When I'm in 1, 0, 1, 0, what's the next state? 1, 1. When I'm in 1, 1, what's the next step? 0, 0.
0.
Yes. Okay, and that's it. This is my state diagram. In the exam is the same thing. Okay, state diagram. But I will tell you what comes in the exam. Don't worry. Okay. This is a state table. Okay. And now I have to write down the state equation. State equations. Okay. Equation number 1 is NA. NA. Okay. Now I have to use K-map. Okay. K-map. So this is A, this is B. 0, 1, 1, 0. Okay. So NA is, can I optimize this? No. So this one is A bar. This one, I use red color. A bar B, right? A bar B. Or this one is A B bar. Am I correct? This is actually A X or B. Okay? So this is NA. The next one is NB. 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 I use K-map. A, A, B, 1 0 1 0 1 0 1 0. This one, can I optimize this? Yes, I can group this, right? What is this? B bar. Okay, B bar. So now I have the state equation already. Finally, I have to draw it. Okay, draw. So I have the A, I have the B, then I have A bar, B bar, A bar, B bar. Okay, so you draw like this, and then you put your flip-flop. This is flip-flop A, flip-flop A. Flip-flop, here you have the Q, and this is your D flip-flop, right? D, Q. Then this is flip-flop B, this is the clock, this is B, Q. Okay. Then you connect the clock to each other, and this is C, L, K. Then this is the N, A. This is NA, this is NB. What is NA? You have the equation, right? A bar B or A B bar or AX or B. So I'm gonna put an X or here. And this is A, this is B. So from A comes here, from B comes here, and this is NA. That's it. Okay. What is NB? NB is B bar. You remember the flip-flop here gives you B bar, right? If you remember, it actually gives you B. Oh, so we don't need to draw this. I confused. We don't need to draw this. Okay. Sorry. Okay. So this is the B bar. I also have A bar here. Okay. So NB is the B bar. NB is the B bar. And this is your experiment. Number, what is it? No, the first one, experiment 1. Okay. So now, what time is it? 11, 12. Okay. Now, do you have to go to another class today? Do you have another class? Because today is not flood online. Can you stay here 5 minutes?
Yeah.
Okay, okay.
Yes, sir.
Those students who want to go, you are free to go. This is being recorded. You can actually come and rewatch it. There is one. So this is actually experiment number 2 finish, not number 1. Okay, but there is a little bit I have to explain. Okay, so if you can come and rewatch this section later. If you have another class, you can go. Now look at this. Let's go to my ISE. Oh, I forgot to run it. Okay, while this thing being loaded, okay, it takes time. Yeah, this is being loaded. Okay, so you, if you were in the lab, I would ask you to go and pick the TTL IC 7474. Okay, and then we have XOR, or you can use AND and OR. And if you set up this, then you believe me, you will. This one should be connected to TTL. You will have a 4-bit counter. Okay. Now I'm gonna explain how you're gonna do the next experiment. Okay. So in your report, what I show you here, right? Put this one for experiment number 1. All right. Plus the thing that I'm going to show you soon. All right. Let me run this. For the next experiment, okay. Now I want you to practice this thing, state equation, everything, right? So for the next experiment, look at this. You are going to have a counter, but this counter does not start. It is not normal counter. It starts from 3, and then the next state is 6, 2, and so on. It's a 3-bit counter. So how many states I have here? You have to count it. It's 8 states. Okay. So I need 3 flip-flop. Okay, so here I had 2 flip-flop. In the next one, I have 3 flip-flop. So 3 flip-flop, you just quickly draw. And then here, be careful, I have the input 2. I have input. So I say I have the input S, and then I have 3, 1, A, B, C, 3 flip-flop. Okay. Then you draw like 0, 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1. Okay. Then you ask yourself, what will be the next state of A, next state of B? This is C. Next state of C, okay? If the start, okay, is not invoked, so maybe I show you here 1, 0, 0, 0 is another row, 1, 0, 0. If a state is 0 not invoked, okay, means you go normal. But if the start, this is the start. If the start S is 1, means the start is invoked. Where do you go? 3. The next state is always 3. So 3 is what? 0, 1, 1. All the way to here, 0, 1, 1. When the S is 1, the next state is always 3. Because you have to go to the start. Start is 3. But let's say when the S is 0, means now you are in normal mode, right? The ABC is 0, 0, 0. Okay, what is 0, 0, 0 is here. What's the next state? When you're at 0, what's the 3, 3, 3, 3. So here I write 3. When I am in 1, you see now 0, 0, 1. I'm in 1. What's the next step?
7.
7, 7. So I'm, yes, 7. So 3 students, hold on, 3 students told me 7. One was who, Pongseri, another was?
Kim Song.
Kim Song, okay, another, I heard the voice of another student too. Only Kim Song?
Yeah,
okay. Okay.
I have my next class now.
Okay, you can go and then rewatch this, okay? Rewatch this. I have this recorded, okay? So 7, you put 7 and you complete this, and then you draw K-map for NA, for NB, NC, the way that I show you here. You get the state equation, and then you put 3 flip-flop, and then you draw the schematic or write Verilog code. Okay, that's it. That's it. If you do it, means you actually fully understand the sequential circuit, and you can design, implement, and work with them. Okay. Now there is only one thing left I have to tell you, so you can actually do this by yourself. Okay. So let's say close project. What is this one? Oh, let me show you the simulation of previous one. This is actually fun. You see, if you do the simulation of, this is big number 9. This is what I want you to show me. Okay. So you see, when the module, the top module, right? When I simulate, it's only clock and reset. So this is important. Pay attention. Now I want to see the signals inside the module top. So I come here UUT, and now I can have the signals. You see, now I know you don't remember this, but these are actually counter. Okay, the counter that we designed. You see, I drag it here, and I said this is digit 1. I select this A, B, C, D, right? Right click, new virtual box, and I say, for example, this is digit first D1. This is D1, and this one I select like this. Okay, new virtual box. This is D2. Now let's. This one is MSB D C B A D C B A. Okay, D C C B A. Okay, and then relaunch. Wait, no, relaunch. No. The students who have class, they can go. This is being recorded. Just come. It's like 5 or 10 minutes more. I have to show this. Okay, so. Pay attention what's going on now. Here I change the radix to hexadecimal, and can you see it's counting 0, 0, 1, 2, 3, 4, 5, 6, 7, 9, and then all the way to 59. To now it's 29. To the whole thing, right? You see? 2, 3, 5. You see? This is actually digital clock. It goes to 59 and then it goes back to 00. Okay? So this is for week number 9. I didn't show you the simulation. Now I did. Let's close this. Only one thing, very small thing left. What time is it? 12:07. Okay, I'm gonna show you. So when you do all those things on paper, okay, now you want to implement this. You want to simulate the 2-bit counter, 3-bit counter. So you create a project. You say, for example, section 641, week number 10. Okay, and everything is same. Then here, the first thing you do is to create a new source, and then you say, I'm actually going to design to enter the flip-flop. So I said, this is my flip-flop, D flip-flop, okay, D flip-flop, D flip-flop, and that's a Verilog module. Next, 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 okay, and then come to my lecture note, and I have given you the D flip-flop. You see here, D flip-flop, D flip-flop. So QD clock. Just type very quick. I'm going to do it very quickly. QD clock. And then you say input is CLK, input is D, and the output is Q. Then always be sensitive. Always. Wait. Always be sensitive to positive edge of clock, because this is D flip-flop, positive edge, it's sensitive to edge, CLK, begin and end, okay? And then when the clock comes, Q becomes D. Simple as that. That's it, okay? Let me check. Let me check. Oh, I have to define this as register too. So output D register. That's it, okay? Now you have actually a flip-flop, a real flip-flop, okay? Register is a memory. Now, this is the part that I want to show you. Otherwise, you cannot do it, okay? Let's say I want to, because now I'm not in the lab, right? You are not in the lab. So you want to show this report to me, so you don't have access to TTL IC. So you want to do it using Verilog and simulation, okay? So what you should do is this. You come and select this flip-flop, and then you go here, and you have to do this, create a schematic symbol. Double click on this, and after this is done, you see the tick, means now I can use this in a schematic. So use the flip-flop, right click, new source, and right click, yeah, new source, correct. And then select a schematic, okay, and say this is, for example, experiment number 1. Next, finish, okay. I'm gonna show you two versions very quickly. So for the schematic, we did this already. You can draw things, right? But now I have flip-flop, so I come here to the symbol, and that flip-flop that I created is called D flip-flop. When I type D, you can see it here, and D flip-flop, and I put it here. You see? And for experiment number 1, I need 2-bit, right? D flip-flop, D flip-flop. Now look at my drawing. Where is it? Here. So look, I need an XOR, right? I need an XOR. So here I go and I search for XOR. This D flip-flop that you see, I designed by myself. Okay, I create a schematic symbol. That's why I can put it there. If you don't do that, you cannot find it. So I put an XOR here. And that's it. So I use wire, add wire, clock to clock, and this one goes to the output. to the input, and this is actually output. This is output. Okay. Now XOR is what? XOR one pin comes from here. Okay. Another pin comes from B. Okay, comes from B, and this one is NA, and B is what? NB is B bar. So I don't have the B bar, so I have to put an inverter. Inverter. Okay, so this is B bar, add wire. And this one is B, that's it. And finally, I use the IO, add input. Input, this is input, okay, and add output. 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 The input is what? Is clock. So here, name is CLK, clock. Okay, and the output is just 2-bit, right? For example, A and B. That's it. Now the simulation of this is on you. You do the simulation. By now you are able to do this, okay? Now so this is the schematic version. This is experiment number 1, and you simulate it, okay? For the experiment number 2 is the same. You can do exactly the same thing. I accept, okay? But you can actually go for Verilog code, go for coding. So VHDL, Verilog module, okay? This is experiment number 2, right? I'm gonna show it to you too. So here we have the clock. Oh, I forgot to use the reset too, but anyway, these are the things that you can just gradually use, okay? So input is clock and reset, okay? So here I want to have 3-bit counter, right? Then how many flip-flops I need? 3. So I have my flip-flop here, okay? So I just copy the definition and I go to Verilog and I paste it here. So let's create 3 instances. This is, for example, flip-flop number 1, okay? Put dot here. This is pinout, dot, okay, and dots. All right. Then I have to connect this to some signals, right? Some signals, right? I copy this 2 more times, like this, like this. This is flip-flop number 2. This is flip-flop number 3. Number 3. And then you just need to, this is actually, I will not tell you, okay? Otherwise, I will, it's like I did everything for you. Then what else you want to do by yourself? So here, go get the equations of N, A, N, B, and C. Okay. And can you see how they are connected? D and Q, right? D is connected to NA. Q is connected to A. So in your code, D connected to NA. Q is A. You have to define them, okay? This is B. This is B. This is NB, next B. And this is C. And next C. You also have here, you have an input, a start, okay? So the only thing, I show you this much, but you have to actually have the equations. You can use data flow to set up the equation, wires, and connect this 3 module, and then simulate. When you simulate, right, I should be able to see something like this, the simulation, okay? When you simulate, I should be able to see something like this. First, I see 3. Oh, first I see 3. Then Where is my lecture note? 3, then 6. Pairs here. I see 3. Wow. I see 3. Then it changed. My mouse is something wrong. Okay. It becomes in your simulation 6. Then it becomes 2. When you simulate 5, and so on.
Yeah.
Okay.
Can
That's
you
it.
check attendance for me?
Can I what?
Check attendance.
Yes, sure. Okay, so this is done. Now, if you, I will do the attendance. Okay, right? If you have
Okay.
any question, hold on. Any question, please contact me during the week, anytime in Microsoft Teams. Any line, any problem, anything that you cannot solve, I will help you. Okay, let's do the attendance. Which one? Who are you? What's your name?
Wasayot. Number 10.
Number 10. Okay. All right. Questions in Microsoft Teams. Good luck to all of you. What? Number 10. Okay. Okay. Bye-bye.
Thank you.
Thank you.
Yes. How about this guy, Vishnu? Kritsapa? Maybe they went to the lab. Okay. Bye-bye. Take care. Good luck. Okay. Bye-bye.